Good morning, everyone. This is an audio recording for the visually impaired student from the book Pradeep's Inorganic Chemistry, Volume 3 by Dr. K. Basim. Magnetic properties of transition metal complexes. Electrons revolve around the nucleus in every atom. A revolving electron, like a loop of current, was shown by the noted physicist Oersted in 1820 to deflect the magnetic needle. When electrons revolve in anti-clockwise direction, the current is clockwise. As a result, the upper face of the electron loop act as the south pole and the lower face act as north pole, as shown in figure 2.1. Does an electron in motion behave as a magnetic dipole and possess definite magnetic moment? If E is a charge on the electron revolving in an orbit of radius r with the uniform angular velocity omega, then the corresponding current produced is I is equal to current by time, that is equal to E by T, where T is the time period of revolution of electron, that is equal to 2 pi by omega, or I is equal to E upon 2 pi upon omega, that is equal to E omega upon 2 pi. Area of the orbit A is equal to pi r square. Magnetic moment of the atom is given by m is equal to Ia, that is equal to E omega upon 2 pi into pi r square. M is equal to 1 by 2 E omega r square. Or according to Bohr's theory, an electron in an atom can revolve only in discrete stationary orbit in which the angular momentum of the moving electron is an integral multiple of h upon 2 pi and where h is Planck constant. Thus MVR is equal to n into h upon 2 pi r. 2 pi. We know nu is equal to r omega, where the value of nu in equation 2.3 we get m r omega into r, that is equal to nh upon 2 pi, or omega r square, that is equal to nh upon 2 pi m. Substituting the value of omega r square in equation 2.2, we get m is equal to 1 by 2 e into nh upon 2 pi m, that is equal to n into eh upon 4 pi m, that is equal to n mu b. Mu b is equal to eh upon 4 pi m. It is clear from equation 2.5 that the magnetic moment of an atom is quantized and the smallest value of atomic dipole moment m is mu b, that is equal to eh upon 4 pi m. This value of m is called the Bohr magneton. Thus Bohr magneton Bm is the magnetic moment of an atom due to the orbital motion of the electron in the first orbit of hydrogen atom. Since the magnetic moment is produced by the moving electrical charge, it is expected that the nuclear spin, the spin and orbital motion of the electron will result in magnetic moment. The nuclear contribution is very small compared to the electronic contribution, therefore the nuclear contribution can be easily neglected. It means that the measured magnetic susceptibility of pure substances are usually associated with the electron. Each moving electron can be regarded as a micromagnet and the total movement exhibited by a substance is a net result of the movement of individual electrons. To define the magnetic behavior of material, it is appropriate to understand a few terms associated with magnetism. Pole strength. The strength of a magnet can be expressed in terms of unit pole. A unit pole is defined as a pole that repels or attracts a similar pole placed 1 cm away from a force of 1 time. Thus, a unit intensity of magnetic field exists at the point and the unit pole experiences a force of 1 time. Pole strength and line of force. A magnetic field of unit intensity is considered to give a unit line of force per square centimeter. If a pole of strength m is enclosed in a sphere of radius 1 centimeter, a total of 4 pi m line of force will come out of this pole. This is because the surface area of the sphere is 4 pi square centimeter and the number of line of force per square centimeter at the surface of the sphere is given by 4 pi m upon 4 pi, that is equal to m. Intensity of magnetization I. It represents the extent to which a sample is magnetized when placed in a magnetic field. It is defined as the magnetic moment per unit volume of the magnet. I is equal to magnetic moment per unit volume. If A is a uniform area of cross section of the magnetized sample and 2L is the length of the sample, then I is equal to m into 2L upon A into 2L, that is equal to m by A. Thus, intensity of magnetization of a magnetic material is also defined as a pole strength per unit area of cross section of the material. Magnetic induction. When a substance is placed in a magnetic field of strength H in gauze or Oersted, the total magnetic induction or magnetic flux density B within the substance is given by the relationship B is equal to H plus 4 pi I. where I is the intensity of magnetization. The expression 2.7 can be rewritten as B by H is equal to 1 plus 4 pi I by H. B by H is equal to 1 plus 4 pi K. The ratio B by H is called the magnetic permeability. Magnetic permeability is the ability of the material to permit the passage of magnetic line of force through it. The magnetic permeability of a substance B by H is the ratio of the density of magnetic line of force within a substance in a magnetic field to the density of the line of force in that field in the absence of the substance. The ratio I by H is called the magnetic susceptibility per unit volume or simply as volume susceptibility. It is a property which determines how easily a sample can be magnetized. It is this property that is commonly measured experimentally. Magnetic susceptibility is commonly expressed per gram as psi as or per mole xim thus. Xim is equal to m by d where m is the molecular weight. The molar magnetic susceptibility is related to the permanent magnetic moment mu b of a pure substance by the relationship xim is equal to n into mu b square upon 3 kt, where k is the Boltzmann constant, n is Avogadro's number, T is absolute temperature in Kelvin, and the permanent moment is expressed in Bohr magneton. Rearranging equation 2.10, one gets mu b square is equal to 3k upon n xi m into t, and mu b is equal to under the root 3k upon n into under the root xi m into under the root t. Upon evaluating the constant under the root 3k by n, we get mu b is equal to 2.828 into under the root xi m into t. Thus, the magnetic moment mu b can be calculated from the magnetic susceptibility using the above relation. Type of magnetic material. When a substance is placed in an external magnetic field between the pole of a magnet, the magnetic field produced by the spin and orbital motion of the electron of the substance interact with the external magnetic field. Different substances show different magnetic behavior when placed in the external magnetic field. On the basis of their magnetic behavior, different material can be classified into the following three categories. First is diamagnetic substance, second paramagnetic substance, and third is the ferromagnetic substance. Diamagnetic substances. Substances which are weakly repelled by the external magnetic field are called diamagnetic substances. Diamagnetism is exhibited by substances which allow the magnetic line of force to pass preferably through vacuum rather than through themselves as shown in figure 2.2a. It amounts to say that in case of diamagnetic substances, the number of lines passing through them is slightly less as compared to the line of force passing through the vacuum. As a result, diamagnetic substances are slightly repelled by an external magnetic field. Diamagnetism is exhibited by all substances with completely filled electronic subshell. Diamagnetism is produced by the orbital motion of the electron of the atom, ion, or molecule of the substance. Diamagnetic effect arises only when the substance is placed in a magnetic field. It is due to the interaction of the applied magnetic field with the magnetic field induced in a substance with completely filled electronic subshell. The induced magnetic field is in case of substance with paired electron is in the opposite direction to the applied magnetic field. Paramagnetic substances. Paramagnetic substances are broadly defined as substances which are attracted towards the applied magnetic field. The number of line of force passing through the paramagnetic substances are much more compared to those that would pass through vacuum as shown in figure 2.2b. Paramagnetism is caused by the presence of unpaired electron. The more the number of unpaired electron in a substance, the greater is the paramagnetic behavior. We know that more of the transition element, including F block element, are known to contain unpaired electron. As a result, transition metal display paramagnetic character. All paramagnetic substances have a net non-zero magnetic moment of its own. Some of the common examples of paramagnetic substances are aluminium, platinum, chromium, copper sulfate, CuSO4.5H2O, salt solution of iron, copper, and nickel, and dioxygen molecule. Some of the paramagnetic substances show complicated magnetic behavior, which arises due to interaction of individual magnetic moment. The individual magnetic moment interact with one another in such a way that so to align themselves spontaneously. Classification of magnetic moment. Type diamagnetism, origin of behavior, interaction of magnetic field with closed electronic shell, magnitude at 20 degrees Celsius, IM, negative, very small, 10 to power minus 5 to 10 to power minus 6, temperature dependence of susceptibility, none, field dependence, no, example NABR, argon, FeCl6 for negative, organic ligand. Paramagnetism, interaction of magnetic field with incomplete electronic shell, positive xim value, small, and 10 is to power minus 2 to 10 is to power minus 3. Temperature dependence of susceptibility decreases very inversely with temperature. Field dependence no. D and F transition metals such as Fe6 3 negative and D3 positive. In addition, to oxygen and NO2. Paramagnetism. Interaction with magnetic field cause parallel orientation of molecular magnet over microscopic region of the solid. Xi value positive, very large, 10 is to power 0 to 10 is to power 2. Temperature dependency decreases because paramagnetic at Curie point. Field dependence, yes. Example, metallic, iron, gadolinium and nickel. Antiferromagnetism. Interaction with magnetic field cause neighboring particle with unpaired spin to interact among themselves. Magnetic susceptibility is value positive, very small, 0.1 to 10. Temperature dependency increase above Tn. It varies inversely with temperature below Tn. It decreases. Field dependency, yes. Example, copper 2, acetate, MnO, MnO2, FeO, NiO, V2O5. Experimental method of determining magnetic susceptibility. A number of methods for determining the magnetic susceptibility are known. The two important methods commonly used are Gauss method and Faraday's method. Gauss method, the method involving the filling up of finely powdered substance to a certain height in a Pyrex glass tube called the Gauss tube. This tube is suspended from one arm of a sensitive analytical balance in a magnetic field and electromagnetic, providing a constant magnetic field in the range 5000 to 20,000 Gauss in generally used. The bottom part of the sample is in the stronger part of the magnetic field, with the top part of the tube is in the zero magnetic field. The whole assembly is housed inside an enclosed system in order to avoid vibration of the suspended sample. A diamagnetic representation of the setup is shown as figure 2.3. The powdered substance in the Gauss tube is first weighed without the magnetic field and then weighed in the presence of magnetic field. In case of paramagnetic substances, the substance will be attracted strongly towards the magnetic field and will weigh more. This increase in the weight of substance is the measure of paramagnetism of the substance caused by the unpaired electron. The larger the number of unpaired electrons in the suspended substance, the greater is the increase in the weight in the magnetic field. In case the substance is diamagnetic, a decrease in the weight of the substance is registered when the magnetic is on. Calculation of magnetic moment. The Gauss method is the simplest of all the method for measuring the magnetic susceptibility. The method measures the force exerted on the cylindrical sample suspended in a non-homogeneous magnetic field of an electromagnet. The force acting on the sample is given by the expression F is equal to 1 by 2 AKH square, where A is the cross-sectional area of the cylinder, H is the intensity of the central homogeneous part of the magnetic field, and K is the volume susceptibility. The above expression of force is applicable only if the measurements are carried out in vacuum. However, since the sample is placed in air, the susceptibility due to air is K dash need to be subtracted from the measured susceptibility. The equation 2.13 is thus modified as F is equal to 1 upon 2 A H square K minus K dash, where K dash is the volume susceptibility of air. The Gauss tube itself is in the form of a hollow specimen and exert a force which is always present. In order to evaluate the exact force acting on the sample, the force developed due to the hollow specimen needs to be subtracted from the measured force. The force acting on the hollow specimen delta is negative because the tube is made up of diamagnetic material. The equation 2.14 is further modified to F is equal to 1 upon 2 A square K minus K dash plus delta, where delta is the force developed due to hollow specimen. For a specimen of constant length and cross-sectional area, the factor A square is constant. If we take into consideration the density of the specimen, it is possible to rewrite the equation 2.15 as 10 raised to power 6 xi is equal to A plus L beta dash F upon omega, where alpha is the constant for the displaced air is equal to 0.029 into 10 raised to power volume of the sample. Beta is the tube calibration constant and omega is the weight of the sample expressed in grams, and F dash is the force on the sample. F minus delta dash, and F and delta dash are in mg. Gauss tube is calibrated by filling the tube with a substance whose susceptibility is accurately known, and the commonly used substance for calibration is deep blue colored compound mercury tetrathiocyanosinate cobaltate 2 HgCOCNS whole 4, its susceptibility at 20 degrees Celsius is 1.644 into 10 raised to power minus 7. Once we know alpha, beta, delta and F on the given sample of the non-weight omega, the volume susceptibility I can be easily calculated from the equation 2.16. It is important to recall that the susceptibility measured of a given paramagnetic substance consists of contribution both from the paramagnetic and diamagnetic susceptibility. The contribution due to paramagnetic susceptibility is much larger than the diamagnetic susceptibility. The correct susceptibility of the sample is obtained by subtracting the diamagnetic contribution. Thus, paramagnetic susceptibility is equal to measured susceptibility minus diamagnetic susceptibility. Some of the inherent advantages of Gauss method are: it requires very simple, easy to assemble equipment. It is reasonable priced equipment. It is easy to handle and use. It requires a large number of the substance, thus an ordinary analytical balance can be used to measure the change in mass. At disadvantage of Gauss method: in spite of several advantages, Gauss method suffer from the following disadvantages. First is it requires large amount of sample. Second is uniform packing of sample in the Gauss tube is not only tedious and time consuming but is very laborious. Consistent results are not obtained if the packing of the sample is not uniform. Second method, Faraday's method. Faraday's method requires a very small amount of the magnetic sample. The sample packed in a quartz ampule is suspended from a sensitive balance in a region of fairly strong magnetic field as shown in figure 2.4. The sample is suspended between the magnetic poles so that the value of product H into dH upon dx is constant over the region occupied by the sample. dH upon dx is the gradient of the field. The whole setup is enclosed in a closed system which can be flushed with inert gas like nitrogen or helium. Diagram 2.4, schematic diagram of Faraday's method. A is the sample, B is the arm of balance, C is stir, and Q is the quartz torsion filament, and T is the torsion head. A sample weighing 0.1 to 10 mg of the substance taken in an ampule of internal diameter 1 mm is placed in a magnetic field of constant gradient dH upon dx. The force acting on the sample is measured directly using a quartz fiber torsion balance and is given by F is equal to m xi h into dH upon dx, equation 2.17, where m is the mass of the sample, xi is the susceptibility of the sample, h is the intensity of the central homogeneous part of the field, dH upon dx is the gradient of the field in x direction. Similarly, the field exerted by the standard calibrant can be measured by weighting the calibrant both in the field and out of field. Generally, the calibrant used is mercury tetrathiocyanate cobaltate 2. Since the magnetic field H and the field gradient are the same in case of the unknown sample and the standard, the force acting on the sample and the standard can be reviewed as H into dH upon dx, that is equal to F upon m into psi for unknown sample, H into dH upon dx into Fs upon ms into xi s for standard. Equating 2.18 and 2.19, we get F upon m xi is equal to Fs upon ms into xi s. On rearranging, we can write the relation xi is equal to F into ms into xi s upon Fs into m, where xi and xi s are the susceptibility of the sample and the standard m and ms are the respective masses, while F and Fs are the respective forces at constant h into dH upon dx. Advantage of Faraday's method. Faraday's method requires a very small quantity of the substance and the sample needed not to be homogeneous. Compared to Gauss method, which requires larger amount 1 gram, this method requires only several milligram 10 mg. Faraday's method gives the specific susceptibility directly. On the other hand, Gauss method gives volume susceptibility. In order to convert volume susceptibility into specific susceptibility, one needs to know precisely the density of the sample. It is difficult to determine precisely the density of the solid because the value of density depends upon the packing of the solid. Disadvantage of Faraday's method. The main disadvantages of this method are: the equipment is very delicate and require great manual skill. Since only a small amount of the sample is used, reaction occurring at the surface of the sample will lead to large error. Relationship between magnetic susceptibility and magnetic moment. The magnetic susceptibility xi m is related to magnetic moment mu by the relationship xi m correlated is equal to n naught mu square upon 3 kt, where n naught is the Avogadro's number 6.023 into 10 raised to power 23, k is the Boltzmann constant, is the absolute temperature, Rearranging the equation to 0.221 get mu square is equal to 3k upon n naught into xi m corrected into t. Mu is equal to under the root 3k upon n naught into xi m corrected into t, that is equal to constant into under the root xi m corrected into t. Constant, here the constant under the root 3k upon n naught is equal to 2.828. Thus the magnetic moment can be calculated from the magnetic susceptibility using the relation mu is equal to 2.828 under the root xi m corrected into t. Variation of magnetic susceptibility with temperature, Curie and Curie-Weiss law. We have learned that magnetic susceptibility varies with temperature and is therefore temperature dependent. It is shown by Pierre Curie that the paramagnetic susceptibility vary inversely with temperature. Xi m corrected directly proportional to 1 upon T and xi m corrected is equal to C upon T, where C is constant characteristic of the substance known as Curie constant and T is absolute temperature. The above expression stating paramagnetic susceptibility vary inversely with temperature is called Curie's law. A large number of paramagnetic substances obey this simple law, especially at high temperature. If we plot a graph between xi m corrected and absolute temperature T Kelvin, a parabolic curve is obtained as shown in figure 4.2a. However, if we measure xi m corrected for a substance at several temperature and then plot one by xi m corrected value against absolute temperature, a straight line with slope C is obtained in figure 5.2b, which intersect the origin. Curie law is followed by substances where there is no spontaneous interaction among the adjacent unpaired electron. In other words, there is no secondary magnetic interaction between the neighboring magnetic center. Such a substance is called magnetically dilute. Although a large number of substances display this behavior, many substances give straight line that do not pass through the origin, rather intersect the temperature axis a little above the 0 Kelvin, figure 2.5a, or little below the 0 Kelvin, figure 5.2b. Such compounds are stated to obey modified Curie equation, according to which xi m corrected is equal to C upon T minus theta, where theta is the temperature at which the straight line cut the absolute temperature T axis. This modified equation is called Curie-Weiss law and theta is called as Weiss constant. Taking this into consideration, Curie-Weiss law, the magnetic moment can be calculated by the equation mu is equal to 2.828 under the root xi m corrected T minus theta Bohr magneton, equation 2.27. Figure 2.6 shows magnetic susceptibility temperature curve. Ferromagnetic and antiferromagnetism. We have learned that the magnetic properties in case of paramagnetic substances originate entirely from the individual magnetic center. It means that there is no secondary interaction between the neighboring magnetic center. Such type of substances are named as magnetically dilute substances. However, there are some paramagnetic substances in which secondary magnetic interaction exists between the neighboring magnetic center. Such substances are called magnetically centered such substances. In such cases, the magnetic susceptibility shows dependence on both temperature and field strength. Two such important type of magnetic susceptibility are called ferromagnetic and antiferromagnetic. The dependence of susceptibility of these two forms are displayed in figure 2.7 and 2.8. A close inspection of the figure 2.7 reveals that there is some discontinuity in the curve at a temperature marked DC on the curve. This temperature is called Curie temperature. Above the Curie temperature, all ferromagnetic substances obey Curie or Curie-Weiss law. In other words, above Curie temperature, all ferromagnetic substances behave as simple paramagnetic substances. However, below Curie temperature Tc, the magnetic susceptibility behavior is different and depend upon the field strength. A close inspection of figure 2.8 reveals a characteristic temperature T and called the Néel temperature. Above Néel temperature, all antiferromagnetic substances below follow Curie or Curie-Weiss law and show simple paramagnetic behavior. It is important to note that below Néel temperature Tn, the magnetic susceptibility decreases with decreases of temperature. It is important to remember that a diamagnetic substance has its magnetic susceptibility independent of temperature. Magnetic moment. An electron has two types of motion associated with it. One of it is going through the nucleus in an orbit while the other is spinning about its own axis. Since electron is a charged species, its movement generates a magnetic field. Thus, electron determine the magnetic property in two ways. The magnetic moment associated with the motion of electron around the nucleus is called the orbital movement, while the magnetic moment associated with the spinning of the electron on its own axis is called the spin moment of the electron. The resultant magnetic moment is the sum of the orbital motion movement and the spin moment of the electron. We have already discussed in the magnetic field of a substance are generally expressed in terms of unit called Bohr magneton, abbreviated as BM. The contribution to the magnetic moment from the spin moment of the electron is called the spin only moment mu. It is numerically equivalent to 1.73 Bohr magneton. The Bohr magneton is defined as 1 BM is equal to Eh upon 4 pi mc, where is the charge of the electron, H is the Planck constant, m is the mass of the electron, c is the velocity of light, and the spin magnetic moment mu s of a single electron is given by the formula mu s is equal to g into under the root s into s plus 1, where s is a spin quantum number half and g is the gyromagnetic ratio. Gyromagnetic ratio, g is the ratio of the magnetic moment to the angular momentum in case of free ion, and the value of g is 2.00023. For all practical purpose, the value of g is taken as 2. Substituting the value of s as 1 by 2 and that of g as 2, the spin magnetic moment for a single electron comes out to be 1.732 Bohr magneton, as mu s is equal to g under the root s into s plus 1, to under the root 1 by 2 plus 1 is equal to under the root 3, that is equal to 1.732 Bohr magneton. For all atom or ion with the more than one unpaired electron, the resultant spin moment is given by mu s is equal to g into under the root s into s plus 1, where s is the sum of the spin quantum number of the individual electron. Since the value of g is taken as 2.0, the equation can be written as mu s is equal to under the root 4s s plus 1. Metal ion of d block element may have 1, 2, 3, 4 or 5 unpaired electron. Consequently, their spin magnetic moment can be calculated by using the equation. One unpaired electron s is equal to 1 by 2 and its value mu s value is 1.732 Bohr magneton. For two unpaired electron s is equal to 1 and mu s value is under the root 8, that is equal to 2.828 Bohr magneton. And for three unpaired electron s is equal to 1 by 2, 1 by 2 plus 1 by 2 plus 1 by 2, that is equal to 3 by 2, and mu s is equal to under the root 15, that is equal to 3.873 Bohr magneton. And for 4 unpaired electron s is equal to 2 and mu s is equal to 4.898, and for 5 unpaired electron s is equal to 5 by 2 and mu s value is 5.916. It is important to remember that the sum of the spin of unpaired electron is equal to 0. There is another convenient way in which the spin only moment can be expressed as mu s is equal to under the root n into n plus 2, where n is the number of unpaired electrons. The experimentally determined value of the magnetic moment of the same transition metal ion are in good agreement with the spin only values. However, in some cases, the experimentally determined value have been found to be larger than the theoretically practically predicted values. This can be attributed to the contribution made by orbital motion of the electron in addition to the spin only value. In cases where both the spin and orbital magnetic moment contribute, the total magnetic moment is given by the equation mu s plus l is equal to under the root 4s s plus 1 plus l into l plus 1, where s is the resultant spin angular momentum and l is the resultant angular momentum quantum number. The experimentally determined magnetic moment of all of the first transition series are summarized in table 2.2 along with the theoretically determined mu s and mu s plus l value. A close inspection of the table 2.2 reveals that the observed magnetic moment value are frequently greater than the spin only value mu s, but are never greater than the mu s plus l value. It clearly implies that the contribution to the magnetic moment due to the orbital motion of the electron is very small. It means the orbital motion are partially or completely constant. It is preliminary because the electric field of the ligand surrounding the metal ion restrict the motion of the electron. Table 2.2 calculated and observed magnetic moment of all metal ion of first transition series. In case of element of the second and third transition series, and particularly the lengthenoid element, the orbital motion is not constant. This is because the 4f orbital are completely filled and are too far inside the overlying 5s and 5p orbital. Thus, the electric field of the surrounding coordination ligand does not restrict the orbital motion of the electron. Therefore, the magnetic moment of lengthenoid ion result into the contribution of both the electron spin as well as the orbital motion of the electron. The intrinsic magnetic moment of atoms and molecule made up of vectorial vectorial sum orbital and spin motion movement of unpaired electron. Three type of interaction are possible: spin orbital orbital and spin orbital interaction. In case of lanthanoid metal ion, all the three interactions play an important role. In such cases, the resultant magnetic moment can be calculated by means of Russell-Sounder coupling, also called LS coupling, by the relation mu is equal to J into under the root J into J plus 1, where J is the total angular momentum, which is the vectorial sum of the total angular momentum L and the total spin angular momentum S. J is a Lorentz splitting factor given by J is equal to 1 plus J into J plus 1 plus L plus S into S plus 1 minus L into L plus 1 upon 2 J plus 1. Using the equation mu is equal to G under the root J into J plus 1 for the trivalent lanthanoid ion, there is found to be good agreement between the observed and theoretical magnetic moment value. If L and S are not coupled to give the resultant J, as in the case with ion of small multiplied separation, spin orbital coupling does not occur. In such a case, both L and J are aligned separately with the external magnetic field, and the magnetic moment values are given by the expression mu S plus L is equal to under the root 4S S plus 1 plus L plus 1. Orbital contribution to magnetic moment. We have already discussed that both the spin and orbital motion of the electron are source of magnetic moment. The total magnetic moment of the material is then sum up of two components called the spin and orbital contribution. Both these contributions are due to the presence of unpaired electron. However, in many cases, these unpaired electrons are the outermost electron under consideration and are not screened by other electrons. In such cases, the spin contribution become important and the orbital contribution may be neglected. The most common example include ion of the transition metal. On the other hand, when the unpaired electron lie well within the ion, are screened by the outer electron. As is true in case of inner transition metal is at lanthanoid and actinoid, the orbital contribution cannot be neglected and must be combined with the spin contribution to give the total magnetic moment. The spin angular momentum of an electron does not depend upon the chemical environment. As a result, the spin moment of the unpaired electron is not perturbed by the change in the chemical bonding of the compound. However, this is not the case with orbital angular momentum, which depend upon the chemical environment. Consequently, the orbital motion of the electron is very much restricted. This causes the orbital contribution to be reduced or quenched in the complex. This quenching of orbital angular momentum can be easily explained on the basis of crystal field theory. The unpaired electron in the first transition series metal ion are located in the 3d orbital. A transition metal ion have 5 3d orbital, all of which possess the same energies and are degenerate. In order to generate the orbital magnetic moment, the electron should go around the nucleus via this orbital. This is possible if all the three conditions are satisfied. Is that first one is the orbital should be degenerate, and second is the orbital should be of a similar shape and size, is that they should be transformable into one another by rotation about some axis, and third is the orbital must not contain electron of identical spin. In a crystal field, the degeneracy of d orbital are split. For example, in an octahedral environment, the 5d orbital are split up into two groups of different energies with T2g, dxy, dyz and dzx, and eg dx square minus y square and dz square. It is this energy barrier that restricts the orbital magnetic movement of the electron. It is important to note that although the set dz square and dx square minus y square orbital are degenerate in the octahedral crystal field, their shapes are such that cannot be transformed into the other by rotation. It means that the condition 2 is not fulfilled. Therefore, the Eg set of orbital cannot degenerate any orbital magnetic moment. Similarly, the Eg set is in case of tetrahedral complexes cannot generate any orbital magnetic moment. The T2G set of orbital containing dxy, dyz and dzx orbital can be easily shown to be condition 1 and 2, considering the dxz and dyz orbital in an octahedral complex as shown in figure 2.9. A rotation of 90 degree about the z-axis interconvert these two orbitals, so that if an electron was initially in the dzx orbital, it could circulate about the z-axis by jumping between dzx and dyz orbital alternatively, and this movement is equivalent to flow of current, which in turn produce magnetic effect. The circulation of current may be either clockwise or anti-clockwise. However, in the absence of magnetic field, the two possibilities are degenerate. When magnetic field is applied and the two direction of circulation possess different energies that causes the loss of orbital degeneracy. Figure 2.9. Circulation of electron density about z-axis is perpendicular to the plane in dxy and dx square minus y square orbital. In brief, dxy, dxz and dyz orbitals are degenerate, and the dxz orbitals can be transformed into dyz orbital by rotating it through 90 degree about z-axis. Now it is the condition 3 that will dictate whether or not the T2G set will degenerate an orbital magnetic moment. Thus, an octahedral complex with D1 and D2 configuration fulfill all the three conditions. However, D3 electronic configuration does not satisfy the condition 3. Hence, D1 and D2 configuration will carry the orbital magnetic moment, but the D3 configuration will not. On the basis of above discussion, one can predict that the metal ion with electronic configuration D1, T2G1 and D2, T2G2 will have orbital contribution, but the complex with D3, T2G3 configuration will not contribute towards orbital contribution. Table 2.3 lists the electronic configuration of the central metal atom in which the orbital contribution is present or absent in high spin and low spin octahedral complexes with D1 to D9 configuration. Table 2.3 Orbital contribution in high spin and low spin octahedral complexes. D1 electronic configuration T2G1 orbital contribution yes, electronic configuration T2G1 and orbital contribution is yes in case of low spin octahedral. Orbital contribution in tetrahedral complexes. When the metal ion is surrounded tetrahedrally by the 4 ligand, the 5 3D orbital split into two sets is the T2G and EG orbital. The energies of E orbital dx square minus y square and dz square are lower than the energy of T2 orbital and dxy, dyz and dzx. Keeping in view the three condition 1, 2 and 3, the metal ion with electronic configuration D3, E2, T21, D4, E2, T22 and D8, E4, T24 and D9, E4, T25 will possess the orbital contribution, whereas metal ion with electronic configuration D1, E1, D2, E2, D5, E2, T23 and D6, E3, T23 and D7, E4, T23 will not have orbital contribution. Table 2.4 lists the electronic configuration of the central metal atom in which the orbital contribution is present or absent in tetrahedral complex with D1 to D9 electronic configuration. Table 2.4 Orbital contribution in tetrahedral complexes. Number of electron D1, electronic configuration E1, orbital contribution no. D2 configuration E2, orbital contribution no. D3 के लिए yes. D4 orbital contribution yes. D5 orbital contribution no. D6 orbital contribution no. D7 orbital contribution no. D8 orbital contribution yes, and D9 orbital contribution yes. A comparison of the data in table 2.3 and 2.4 with that of table 2.2 reveal that in cases where no orbital contribution is expected, the magnetic moment value differ only slightly from the spin only value. This explains why in tetrahedral nickel 2, octahedral cobalt 2 and octahedral iron 2 complexes the magnetic moment is higher than the spin only magnetic moment. Further inspection of table 2.3 reveal that an octahedral nickel complex and a tetrahedral cobalt 2 complex will have the spin only magnetic moment. However, in reality such a complex exhibit a magnetic moment higher than μs. This is because the excited state of this complex carry the orbital magnetic moment. In a system having such an excited state, the spin orbital coupling bring about some mixing of the ground state with the excited state, thus forcing some orbital contribution. The magnetic moment in such cases can be calculated from the following formula: mu effective is equal to μs into 1 minus alpha lambda upon delta, where μs is the spin only moment and lambda is the spin orbital coupling constant and delta is the difference in the energy level between the ground and higher state, and alpha is the constant depending upon the spectroscopic term. Table 2.5 gives the value of lambda and alpha for a few transition metal ion. Table 2.5 spin orbital coupling constant lambda and alpha value of some transition metal ion. Titanium 3 plus stereochemistry tetrahedral, vanadium 3 plus tetrahedral, chromium 3 plus octahedral, chromium 2 plus octahedral, manganese 3 plus octahedral, iron 3 plus manganese 2 plus, iron 2 plus, tetrahedral, cobalt 2 plus, tetrahedral, nickel 2 plus, octahedral, copper 2 plus, octahedral. It is clear from the table 2.5 that the value of lambda is positive from D1 to D5 and negative from D6 to D10. This clearly explains why the magnetic moment value determined in case of copper 2 complexes are larger, whereas in the case of chromium 2 complexes are smaller than the spin only value. Orbital contribution in complexes of lower symmetry. We have already noted that the probability of orbital contribution is less if the symmetry of the complexes is lower. In case of square planar or square pyramidal complexes, the orbital contribution is possible only in case of D2 and D4 electronic configuration. In case of trigonal bipyramidal complexes, the orbital contribution will be observed in case of electronic configuration with D1, D3, D4 and D5, and the orbital contribution in case of dodecahedral will be observed if the electronic configuration is D7 and D9. Temperature independent paramagnetism TIP. A number of compounded compounds are known that shows a weak paramagnetism in spite of the fact that their ground state do not have unpaired electron. Two such examples are provided by the permanganate ion MnO4 negative and the hexaamine cobalt 3 ion CONH363 positive. Such systems are not expected to show any orbital magnetic moment and are therefore likely to be diamagnetic. Since this species display weak paramagnetism, it may arise by coupling the ground state of the system with the excited state of higher energy under the influence of magnetic field. Because of coupling, the complexes may have some orbital magnetism large enough to cancel out the internal magnetism. Since this paramagnetism does not depend upon the thermal population of level, it is commonly referred as temperature independent paramagnetism or simply TIP. Temperature independent paramagnetism TIP, likewise diamagnetism, is not due to the magnetic dipole within the molecule. Instead, it is induced when the substance is placed in the magnetic field. This induced susceptibility of the ground state is temperature independent. The magnitude of magnetic susceptibility of TIP is of the same order as that of the diamagnetic substances. The chapter is end, and thank you.